Okay, we're back now looking at the electrophilic addition to dienes. The question is, how do we get these two products? We recalled Markovnikov's rule, which said to us that we're going to form the most stable carbocation, and that's perhaps a different way of formulating it. Of course, when Markovnikov formulated his rule, he didn't know about carbocations, he just knew that the halogen went to the more substituted carbon atom. But we know today that the reason for that is in the mechanism. So I'm going to try and switch colors here. I'm not sure how different that is. I'm learning this as we go along with this first lecture here. The pi bond of the diene acts as the nucleophile. So I'm going to write a big capital N and circle it to help you identify these as we go along. Because mechanisms, and by the way, what we're looking at now is the mechanism. And this is what we call an arrow pushing mechanism. So the pi bond acts as the nucleophile, and of course HBr is the electrophile. You protonate the double bond, you break the bond between hydrogen and bromide, and the product of that is the more stable secondary carbocation. So this pathway to form a primary carbocation does not occur because that carbocation is just too unstable. And if you recall, right, tertiary carbocations are more stable than secondary carbocations that are much more stable than primary carbocations. Okay. So we have formed a carbocation, but this carbocation, it turns out, is special. You need to recall for this discussion resonance. Okay. Can you draw a resonance form of this carbocation? Now, let me remind you of the resonance arrow. It's a single line, double-headed arrow. Mine's a little imperfect there. We can live with imperfections for organic chemistry. So can you push the arrows for resonance of this carbocation? Well, hopefully you came up with something is a resonance form. Now, does that mean that this is a primary carbocation and that's a secondary carbocation? Well, again, I like to take this as a point of emphasis for us. Remember, resonance forms are just how we as human beings are able to process these quantum mechanical objects called electrons. You remember Heisenberg's uncertainty rule? Can anybody recall that? Basically, an electron is moving so fast that the more we know about its position, the less we know about its speed, and vice versa. And as they say, Heisenberg rolls over in his grave every time an organic chemist pushes an arrow, like we localize them and know where they are. The other thing about resonance forms is, of course, the molecule is not some percentage of time here and some percentage of time here. The electrons are distributed, and as I like to say, the molecule is the molecule is the molecule for your generation. And whether we draw it with the carbocation at the primary position or the carbocation at the secondary position, the molecule doesn't know the difference. This is again so that you and I have an accounting system to keep up with the electrons. It's again for our benefit. Of course now what this cation is called, anybody know that one or recall that one? This is an allylic carbocation. Now, why is it called allylic? Because the position next to a double bond, so let me go here, here's an allylic position, and this position is also allylic. Now, the carbocation is next to this, and so we call this an allylic carbocation. But this resonance form is again very useful to us because I lost something. When I protonated the double bond, what did I forget? I didn't put up Br minus. Now, I'm not left-handed, so this may be a little awkward. Bromide is there to balance the charge. Remember the principle of electroneutrality. We can't separate charges, not easily. When we do that, it results in things like lightning. Lightning is separation of charge on a planetary scale. We don't want to have lightning in the organic lab. That would be a very dangerous thing. So there's not separation of charge for most chemical reactions. Separating charges is a very, very high energy process, as you can imagine from your experience with thunder and lightning. Okay, so what's useful about this resonance form, and I'm going to switch colors again here, is that the bromide can attack either end of the allylic carbocation. And if it attacks this end, as I drew with the blue marker, it produces the 1,4 product. In contrast to that, let me grab another color here. If the bromide attacks the other end of the allylic carbocation, you see it produces the primary, the 1,2 addition product. So this is the mechanism of electrophilic addition to dienes. This is our simplest diene that we deal with in terms of 1,3 conjugated dienes. So these are conjugated dienes. Recall that. Let me review for us for our mechanism now. And I like the orange color there, so I'm going to make use of it. I put a big N by the pi bond as the nucleophile, and remember, HBr was the electrophile. It created a mu carbocation or a mu electrophile here at the allylic carbocation, and of course then a new nucleophile there and the bromide. And as the bromide reacts either at the terminal end or the internal end of the allylic carbocation, I produce the 1,2 or the 1,4 product. Okay, so this is the mechanism. It's a great review for us. If you haven't been pushing arrows in a while, then this is good practice for you. And let me emphasize for you again, for organic chemistry, pushing arrows is very important for understanding how electrons flow and understanding the fundamentals of these chemical reactions. Because we want you to learn the basic concepts and ideas and be able to apply them to a system that you've never seen before. So